Greetings and welcome, friends. We're continuing our look at 6.3 exponential functions. I'm just going to show you example 7. Maybe you have time to look at the monitoring progress question that follows it, which is number 10. So it says this, the graph represents a bacterial population Y after X days. All right, so my x-axis is number of days. The population is like this, and I don't know if you guys knew this, but as long as there are sufficient resources, a population grows exponentially, all right, not linearly. And that's so one of the things now that you know. Perhaps in like a biology class or something as well, you'll end up looking at data like this as well. Okay, so here's what it says. Write an exponential function that represents the population. Oh dear. Oh dear. Okay, so for part A, well, we've got this graph here. We've got our data. We've got a line drawn. But what if I want an equation that represents the population Y after X days? So what I'm thinking about, the way I'm perceiving this, is I'm thinking about, right, the y equals a times b to the x sort of situation, right? Okay. So I'm thinking y equals a times b to the x, and theoretically we could also have the minus h and the plus k, but I don't think those are going to show up in this problem because I happen to know they won't. So the first thing we should figure out is the b value and figure out what multiple these are going up by for each of their corresponding intervals. All right, and one of the ways you could do that is with a table, and that might be helpful. Let's just compare x's and y's, and we'll just do like table style, and then I'll show you how you also could have possibly read that off the graph. So the first point I had was 0, 3, so I'll write a 0 and a 3. All right, then I had a 1 and a 12. All right, 1, 12. So that means 1 day later, their population was 12. And it doesn't say that this was 12 in thousands or millions, so I'm assuming that literally that's what they mean, is just 12. On day 2, it was 48. Okay. On day 3, it was 192. And on day 4, it was 768. So, notice that the x intervals are in fact consistent. They're going up 1. All right, plus 1, plus 1, plus 1, like so. And now the question is, what is the pattern for the y's? What is the pattern for the y's? So to go from 3 to 12, I could have added 9, but that would have been, if I'm doing adding or subtracting, that would have been a linear relationship, and I already see that this is exponential, which is why I'm even thinking of this equation. So 3 times what is 12? Or what is 12 divided by 3? Friends? Yeah. 4. So that means that 3 times 4 was 12. And let's see if this pattern persists. What is 12? Is 12 times 4 48? 4 times 10 is 40. 4 times 2 is 8. So yeah, 48. All right. Is 48 times 4, 192. Feels like it. And it is. Hooray. So it looks like we found our pattern. And if I multiply that by 4, I get 768. So the base, the b value, all right, is going to be that 4 number. b equals 4. All right, that's the rate that it was growing by, the factor that it was being multiplied by. So the rate was 4. But now remember that 4 to the 0, all right, my y-intercept is typically 1. okay? Typically 1. However, here the y-intercept is 3. So that means that my a value must have multiplied the 1, right? Right, 4 to the 0 is equal to 1, multiplied by a ended up equaling 3, all right, is kind of what I'm thinking about. So I'm like, okay, what's happening to a? What was a that it suddenly made that into 3? And the way I could kind of think about that, right, I just kind of plugged in what I knew. I had 3 for y, I had 0 for x. Well, one of the weird things that we recognized about these exponential patterns is that it's equal to 1. All right, because the pattern would have been 4. 4 squared is 16. 4 to the third is 64. And the pattern, right, is multiplying by 4, but backwards it's dividing by 4. And 4 divided by 4 is 1. So yeah. And so what I end up getting is that a equals 3. And you also can determine that just based off of the y-intercept. As long as there was no up k and over by h, the y-intercept is always going to be whatever the a is here, okay? All right, so my equation is y equals 3 times 4 to the x is the equation of the population of this bacteria after X days. But now they asked us a question for part B. They said, okay, find the population after 12 hours. Now the problem is my X's are measured in days. What is 12 hours measured in days? Half of a day. Okay, so for part B, 12 hours is equal to 0.5 days. Right, or half of a day. You guys agree? All right. So that means I would have to plug in 0.5 for x, and I would get y equals 3 times 4 to the half, or 0.5. 4 to the 0.5, or 4 to the half. Now, we ended up skipping properties of exponents. You'll pick those up in Algebra 2. But it turns out that 4 to the 1/2 power is 2. Is a weird thing. And that, don't just assume that means 4 divided by 2. Because that's actually not exactly what's happening there. But y equals 3 times 2 is 6. So that means after 12 hours, the population of the bacteria is 6. All right? But then they asked another question. They said, what is the population of the bacteria after 5 days? So I can't just read it off the graph. So if x equals 5, I would just plug in 5 in my equation. Y equals 3 times 4 to the 5th. And 4 to the 5th is 1,024. And 3 times that number is 372. All right, so I can use my equation now to predict the future population of this bacteria, even though my data didn't originally give me that information. All right, so that's one of the benefits of real-world problems like this is you gather data, you write an equation that models that data, and then I can now predict, right, future events of, hey, the population should be around this if conditions remain the same. All right, and that's one of the benefits of mathematical modeling and being able to have found an equation for this in the first place. All right, let's take a quick look at Monitoring Progress 10. All right. Similar idea. It says a population of bacteria, or a bacterial population, y, after x days can be represented by an exponential function whose graph passes through this and this. Wow, they only gave us 2 points? Oh dear. Now, they also gave us the clue exponential, okay? So it says, write a function that represents the population. So the question is, all right, so if I make like a little table of values sort of thing, 0 and 100 went to 1 and 200. So the population, I was just going to give us the answer, I realized. It doubled, right? So over an increment of 1, the population multiplied by 2. And the reason I didn't need more points to recognize a pattern is because they told me it was exponential. So that means on the next day, what would you expect the population to be? No, double, right? So I would expect 400, and then 800, etc. Right? So because it's exponential, that's what I would predict, and I know that the value of b is going to be 2 now. So b equals 2 because of this. All right, I also know that the y-intercept was 100. The y-intercept typically would have been 1. And so check this out. In the equation, y equals a times b to the x. Let's plug in what we know and solve for what we don't. So if I plug in 100 for y, and you'll recognize the pattern eventually, and you don't have to plug it in every time. B is 2, I just figured out, and x was 0. And so 100 equals a times 2 to the 0. Anything to the 0 is 1, therefore a equals 100. All right, in general, your y-intercept is going to be your a value every time, unless there was a horizontal or vertical shift, okay? And so our equation now is going to be y equals 100 times 2 to the x. So there's our equation for this particular population of bacteria based on just 2 points of data and the knowledge that this population grows exponentially. All right, so now part B, it says, find the population after 6 days. You guys think, what am I plugging 6 in for? Well, x was the number of days. So y equals 100 times 2, and I'm plugging in 6 for x, so to the 6th. All right, so y equals 100 times 2 to the 6th. And I get, actually, let me figure out 2 to the 6th first, so I can do this piecemeal a little bit. So that's 100 times 64. 2 to the 6th is 64. So y is equal to 6,400. So in 6 days, this population is 6,400. But now they asked the question, that I find interesting. Part C, does this population grow faster than the one that we just looked at in example 7? Now, what are our thoughts? This one started higher, right? This one started at 100. So the one that we just looked at started at 100 and then was 200 on day 1. Well, or it started at 3 for this one. Right. Oh, right. 10 started at 100, and question 7 started at 3. But the issue was this one was doubling every time, right? On day 2, it was at 400. On day 3, it was at 800. So which of these graphs is bigger? Or which is growing faster? Okay, now in terms of which is bigger, the bigger population right now is 10. But as far as which grows faster, growth has everything to do with the value of b. Yeah. Right. It's bigger. But will that always be the case? Because on example 7, it was growing, it was quadrupling every day, whereas in question 10, it was only doubling every day. So it grows slower than example 7. Slower because 7 was quadrupling every day, right? Times 4 each day. And this was, and 10 was only doubling each day. And on our graph, we don't actually see that outcome, all right? We don't see that example 7's bacterial population will end up overtaking it. But I can show you real quick on Desmos. Let me pull this up, and then we'll call it a lesson. All right, so here's the population. Let me actually change our Y scale significantly here. We'll do something like that. All right. So this is example 7's equation. Let's do monitoring progress's equation. So that was y equals 100 times 2, right, to the x. Oh dear, I just did 2 x's. That's crazy. There we go. So we can see, okay, right, like you were saying on day 3, this was like, you know, somewhere, what was it, day 4? When was it, 700 something? Yeah, right here. So you said here, this one's only 786 or around there on day 4, whereas the blue graph is taller. But notice in terms of growing more quickly, this one actually is growing slower. It's less steep right here, right? Would you agree that this blue line is steeper than this red curve? But notice that this red curve suddenly starts picking up steam, and it's all like, I think I can, I think I can, I think I can, I think I can. Oh dear, they're getting closer to each other. Let's see, let me zoom out. Oh, what? They intersect. And now the red line is bigger. It's growing faster. That's crazy. That's craziness. Here, let me change the Y scale, because that's the one that... All right, so I can smush that down a little bit. And you can see that, yeah, at a little after day 5, they meet, and they both have populations of around 3,333. And then the quadrupling population does overtake it, and we'll just get bigger and bigger, faster and faster, right? And we'll note the blue one will never catch up. Never, ever, ever. So yeah. So that's interesting. Actually, yeah, just to show that the blue one, with respect to the height of it, the more I smush it down, you'll realize, right, it actually never will overtake it. That quadrupling, right, if you had a choice, if you had a bank, and you're like, all right, I have $3, and this bank will quadruple my money, is that a better option than them giving you $100 and only doubling your money every day? And at first, you're like, $100 sounds great, but the quadruple power is going to eventually overtake it and be a way bigger deal. All right, well, thanks so much for watching, Internet friends. Have a great day. Bye-bye.